we start? Yeah. So hi, my name is Alex. Just Alex is fine. You don't have to remember my surname. Hardly ever anybody gets that right. And so I'm actually working at Oracle at a project called Graal and Graal VM. I'm going to present some of the work we did, which is relevant in the context of Scala collections, and this is joint work with these people here. Some of them are actually going to be on the conference these days, so you might also want to talk to them. As an Oracle employee, I'm supposed to give you this safe harbor statement, which basically says that this is my opinion and not a description of a future product. So that I'm okay. Now that that's out of the way, so what is this presentation going to be about? So it's basically three statements that we're kind of trying to make with this paper. The first one is that a JIT compiler can make Scala collection operations optimal. The second one is that usually, so this is a rather bold claim, right? But we try to give an intuition that for this, a JIT compiler is usually a better choice than a static compiler. And I'll discuss why with concrete examples. It's not a proof, it's just an intuition. And the third one is that there are specific optimizations which are more easily done by a static compiler than a JIT compiler, and I'll explain which ones and why. Okay, so I mentioned the word optimal. When I say optimal, I mean it's a program that has the same performance compared to optimal handwritten code with while loops, if statements, stack local variables, and array operations. And this is kind of contextual because I'm not talking about the assembly that gets generated from this, but I'm assuming that once you manage to transform your collections code to something with this intermediate format, you're going to have an equivalently efficient backend which will produce good assembly code for you, right? And even if you don't, it's not a completely solved problem, but it's orthogonal to what I'm going to talk about in this talk. And concretely, I'll talk about high-level optimizations. And this is the outline of my talk. Consists of 4 parts. The first is high-level optimizations in Graal. Then I'm going to present 2 case studies on programs using fold left and a program using map. And then I'll talk about performance of these programs. So I'll first give an overview of high-level optimizations in Graal. And so you should know, as I will show in a second, the Graal uses its own intermediate representation based on the sea of nodes representation, but while I'm introducing these optimizations, I'll show you equivalent Scala code so that it's easier to follow. So I'm not going to talk about all the optimizations that we do, just the most relevant ones for this talk. The first one is inlining, and this is best demonstrated on this simple program where you have 2 methods. One is called square, which takes a double and returns the square of a double. And the other one is called TSS, total sum of squares, which given a list of doubles returns a double which is the sum of all the squares in that list. So if the list is empty, it's 0. Otherwise, it's a square of the head plus recursive call on the tail. And inlining does the following. So it's not completely trivial because it's not just a simple rewrite of SQ to the expression on the right, because if the argument to this thing is a non-trivial expression, then you should first store the result. But it is kind of easy to do inlining, right? Once you have a specific intermediate format. One thing that's not easy is deciding when do you actually do inlining, right? And in fact, some of the researchers like Simon Peyton Jones described it as a black art in one of their papers, because deciding when to inline is anything but simple. And we actually use some quite involved heuristics to decide when to inline functions. I'm not going to talk about them as part of this talk, but it will be future work, or we can just talk offline. The other optimization that I want to mention is polymorphic inlining. And what's specific about the previous program is that this square call that we inlined is a direct call. It means that you know exactly what the implementation is. But that might not be true in general, as shown by this example here, where you have TSS, which takes a generic Scala sequence and returns an int, which is a total sum of squares. And then we implement this method basically by calling the fold function from the standard library, which takes an initial value, and then to the accumulation, that's the square of the current element, right? And here we don't know what the implementation of sequence is, so we don't know what to actually inline. But one of the advantages of a just-in-time compiler is that it can tap into VM functionality to figure out what the receiver type profile is. And concretely in this example, it has information, it has access to a table which is basically telling it at this point in the code, at this call site, a list of integer occurs 62% of times, an array ops object occurs 34% of time, and for example a vector occurs only 4% of time. And based on this information, a compiler, in our case, Graal compiler emits a type switch at this point, where it sorts the different cases in the order of their appearance in this receiver type profile table. And what's important to say here is that these folds now in these matches, in these cases of the match, are now direct calls, which means that they can be inlined. We know exactly what the implementations are. Next, and a JIT compiler has access to these receiver type profiles, which is something that typically a static compiler does not have. A next important kind of optimization that we do is called canonicalization. Basically, this is a group of different optimizations that we apply to the intermediate format to simplify it as much as possible. So for example, in this example, we have a list of 1 to 3, which is applied to actually, there should have been a nil here, I just noticed. Anyway, this list is stored into a sequence of integers. Then we called a fold on this sequence of integers. The sum that we get back we square, and then we add this to 2 times this variable p. And so there's a range of different optimizations that we do here, and they're really sort of Graal is designed as a framework for adding these optimizations. Really, if you have any kind of a special node in the intermediate representation, you can insert a rule saying, how can I rewrite myself? So just to give you a couple of examples, one of them is this classic optimization used for the SSA form called global value numbering, where basically it's basically common sub-expression elimination. So if you had something in the program that you already computed, basically you can detect this and just rewrite this node to the previous value. Similarly, we use like a range of different optimizations like strength reduction, meaning if you have 2 times something, you convert it into a left shift. Then so we also do data flow analysis at this point, meaning that even if this is statically marked as a sequence of integers, we can figure out from the structure of the code that this should always actually be a list. And this means we can turn polymorphic call sites into monomorphic call sites. And there's a range of different optimizations that are specific to JVM, but I'm not going to talk about all of them here. Just to show you that this canonicalization is many different simplification rules which are triggered by localized patterns in the IR. So you ask each node, take a look at your surroundings and try to replace yourself. And this procedure, it's usually monotonic and it converges after a while when you trigger it. And another important optimization here in this context is partial escape analysis and Scala replacement. And this is best shown on this example of the total sum of squares method, which this time takes an array of integers, and then we create an iterator this time. And then you can see here the constructor code of this iterator, which has been, let's say, inlined at this point, which sets the current index of the iterator to 0. It stores the array, and then we initialize some sum variable, and then we call hasNext on the iterator, which when inline becomes this check is current less than array length. And then here in the body of the while loop we call next, which has been inlined and is actually a read from an array and an increment of this current field by 1. And basically what partial escape analysis and Scala replacement does, it's basically a form of a read elimination, because by analyzing this code you can see that every time you call it.array here, it must be the same value that we previously wrote in this line. So that means that you can replace this it array with just a. And similarly, you can replace these occurrences of it.current with a new variable which you initialize to 0. And if you do all these things and then you reason about the fact that this object that's been allocated here never escapes this function, then you can replace those reads and writes, and then your object allocation becomes dead code and you don't need it anymore. And you arrive at code like this. Okay, so there's actually a paper about this and showing why this partial escape analysis is more powerful than standard escape analysis from Lukas Stadler and other authors. So you can take a look at that. There are a bunch of other optimizations, such as path duplication, which actually is somewhat related to splitting that Nate Nystrom talked in the previous talk. We do that to a certain degree, but it's not like a general framework. It's a specific phase in the compiler, which is a fixed set of rules. Then we have loop peeling. We have something called dominator conditional elimination, and there are a bunch of other optimizations. They're not maybe relevant for this talk. And now I want to show you a case study with fold left. So let's take this following fold. Let's observe the following fold left function from the standard library. So if there are any collections experts in the room, can you tell me on which trait was this fold left defined? Sequence, index sequence, sets, maps, iterable, traversable. No? Sorry? That was an answer? No, so this one is defined on index sequences. So basically, the way it's defined is that this fold left calls a recursive, tail recursive function foldle, which takes an argument 0 where you start and a length of the sequence where you end, and these two things for the fold, or arguments for the fold. And then in the tail recursive method, we call the apply function on the sequence to get the element at that position S. So you can see this is an index sequence probably because this is supposed to be an O of 1 operation. So anyway, this is the implementation of fold left. It's actually marked as tail recursive, meaning that the Scala compiler will convert it into an equivalent while loop. And now we have a concrete program which calls fold left with the initial value 0L and then passes a lambda which just sums two values together. Okay. This is 10 minutes left or 10 minutes into the presentation? Wow. Okay. So this is the Graal IR. Basically, I'm not sure if you see it very well, but basically this little program that you see here in the source code of Scala, it actually gets transformed by the Scala compiler into something like this, where basically we cannot call the fold left method directly on the array because that's a JVM array. So that means we need to create this array ops object. In this array ops object, we can call fold left on that, but we cannot just, so this should have been Z here, sorry. We cannot just pass a primitive value into fold left because it expects an object after erasure. So it means that this value needs to be boxed first. We need to actually create an object from the lambda. And then when we're done, we cannot just return the result. We need to unbox it, convert it into a primitive value. And these are all the overheads which are implicitly added when you call the fold left. And if you take a look at this graph for a second, then you can see that this is exactly this is the graph of this compute sum method. And this is exactly what it looks like. So these nodes on the left, connected with red arrows, with red lines, are the control flow in the intermediate representation. And these are creation of an array ops object, the call of the array ops constructor, boxing of the initial argument, creation of the lambda, this is the actual call to the fold left. And finally, there's an unbox to long call to return the result. And basically to optimize this, so you can see actually in this initial graph, there's not much to optimize. Out of these optimization rules that I was talking about, there aren't actually many of them that you can apply here. And since just-in-time compilers are usually based on procedural analysis, the way that you trigger and enable new optimizations is by inlining. So this is what we do. We start by inlining, by building the call graph of the method. And we see that basically this initial method then calls fold left, calls unbox to long, and then you can see these special cutoff nodes which exist in the call graph, which basically denote the places in the call graph where you stop exploring it, because in a just-in-time compiler you cannot really explore the entire program. You have to decide when to stop. And we have a reasonable heuristic which tells us basically when do we stop. Then we have this unbox to long call here, which doesn't have any calls beneath itself, and this is a reason, and since it's very small, this is actually a very reasonable candidate for inlining. So we inline this immediately. We also have some polymorphic calls in the call graph, which we encode with these type switches here. And this is what it looks in the program. So this node here wasn't explored. This one here will be obviously inlined. And here, these points are type switches. And what we do now is that we inline this call here in the first phase of inlining, and then we propagate the type information through the call graph. And when we do this, basically deeper in the call graph, we know that these nodes are no longer polymorphic. These calls are not polymorphic, but they're direct. And this is why they become cutoffs again, and they get re-explored in the context of this new type information. So, and then we continue exploring the call graph like this and propagating the type information through the call graph. And at some point, we actually, in this case, explore the entire call tree. And when we do this, we can completely inline the expanded part of the graph. And at this point, we arrive with a rather complicated graph, which I'm not going to explain here because it's really hard to follow. But if you start applying the simplification rules and canonicalization and partial escape analysis, then eventually you will arrive at a simple program. So for example, if I show a Scala representation of the program again, you can see that in this loop we actually have to, at a low level, have some kind of a check that checks if we're out of, if we should throw an array index out of bounds exception. But then by applying canonicalization and analyzing the fact that we are in a loop where we actually know that this index of the array is less than the end of the array, then we can completely eliminate this check. We hoist it out and eliminate it. And then similarly, at this point we have this new array ops object created, but we actually always access its fields, which we know statically what they are. That means we can apply partial escape analysis, and in the end, finally, we arrive at this very simple loop. And this actually corresponds to this program, where you can now clearly see there's a loop begin, there's an if, where you should you exit the loop or should you stay inside. If you stay inside, you read the array, and then you go to the loop end and you rewind back. All these nodes on the side, they're called floating nodes. I can talk offline a little bit more if you're interested about how this works. And the point here is, one important point that we make is that because we have access to receiver type profile, then if this compute sum method gets not an array, but some kind of a sequence whose top type we don't exactly know, then we can emit a type switch like this, and we'll exactly arrive at the same code as before. And now a very short case study for map is the following. So if you write a program which takes an array and calls map every element plus 1, then at some point during compilation, after you inlined everything, you will arrive at the compiler graph that looks like this. So it basically loads a field which is an array, then executes this load indexed node, which is basically an array read. And then after that, it needs to execute some guards which check, first of all, is this a class cast exception? Should I throw a class cast exception if the class is not right? And should I throw a null pointer exception if the value from the array is null? And only after that can this value be unboxed. And why do we get to this code? Well, basically, if you take a look at the array buffer class, it's not specialized. It's very generic, and the array that it's stored inside is an array of objects. And it means that at some point in the implementation of the map function for the array buffer, you'll arrive at something like this. You're taking a look at the element at position I, and you're casting it from an anyref to a generic type A. And then you're applying a generic function from A to B to this element, and you arrive at the resulting element. And if you inline all this, basically you'll get back a read from an array which gives you an object, and then you have to read the value of that object incremented by 1. And this is actually the body of our function. So this we can inline, but we cannot really get rid of this object because it's already in the array. And similarly, when you're storing the result of this operation into a result builder abstraction from the Scala collections, then you will at some point have to call this result plus equals y. And after you do sufficient optimizations, you'll see that you'll arrive at the mapped value, which is a primitive type, meaning that it's not boxed, but to store it into an array of objects, you need to box it again. And this is not really something that we can get rid of. And this is kind of a premise in this paper, is to say that optimizing data structures is something that the just-in-time compiler typically doesn't do, because that would require a whole program analysis. And that's not something that a just-in-time compiler has sufficient time, basically, to do. It has a very limited time budget to compile a method. This is not to say that a just-in-time compiler never does whole program analysis or doesn't have some other techniques to achieve this. For example, you have shape analysis for dynamic languages, which is an optimization which assumes and speculates on a particular shape. We could do something like this. It's unlikely that we would do it. And this is actually one of the points that we wanted to make in the paper. If somebody wants to focus on optimizing Scala collections, then static optimization of data structures, I personally think that it's a worthwhile area for getting performance. Okay, so and speaking of performance, basically we had a bunch of micro benchmarks in the paper, several larger benchmarks, and these are all involving Scala collections. And then separately from this, we also evaluated this compiler on Spark RDDs and some programs involving that. And you can see, basically, compared to the standard hotspot C2 compiler, which is not as aggressive in applying these optimizations, we get a 17 times speed improvement for fold left. And for map, for the very reason I was talking about, this boxing that we cannot eliminate, we only get about 2 to 2.5 times improvement compared to C2, and that's still almost 8 times slower than what it could be if you write manual code. There are some benchmarks which are less dramatic, like filter, group by, and copy to array. Actually, here our performance difference is much smaller because we allocate less objects, and actually for filter we don't allocate box objects at all. And there's one very dramatic difference where we saw 29x difference between C2 and Graal. It's the find operation. Also had standard deviation. One thing that's important to say is on these larger benchmarks, we saw differences. So we had 4 benchmarks, k-means, histogram, mnemonics, and a SAT solver. We saw differences between 1.1 to 3.7x when we applied these optimizations. And we also had 8 Spark benchmarks, which we describe in the paper what they are. Basically, we had a performance improvement of around 1.2 to 1.8 on a range of different benchmarks using Spark RDDs and its machine learning library. And that's it. So thank you. And I'd be happy to take your questions.
So have you tried doing benchmarking on even larger projects, say the Scala compiler?
Scala compiler?
Yeah.
Yeah, so the Scala C compiler is actually a part of this Scala. Sorry. Okay. So the Scala compiler is a part of this Scala da Capo benchmark suite. So we regularly actually benchmark against this and a couple of other benchmarks which are on Scala only and are a part of this suite. I don't have the numbers here, but I can show you offline on our benchmarking system what the differences are. Actually, we're a little bit in front of C2 by some 20 to 30% depending on the benchmark.
Nice. Yeah. Another thing is, so I think one of the big performance issue with the Scala collection libraries is cooperative equality. Have you done any work on whether in Graal it could be faster or?
So can you again repeat?
Cooperative equality.
Cooperative equality.
Yeah.
I'm not sure what it is.
In Scala, when you use call .contents on a list or something, it's going to use the Scala implementation of equality comparisons, which means that, for example, an int of 0 is equal to a long of 0.
Okay.
So and it has
Is it driven with a type class or?
No, it's driven by the implementation of a correction which is equal, which is translated to Scala runtime dot equals.
Okay. I mean, but that's something. That's a code that's generated by the Scala compiler, right?
Yeah.
So that would basically be either a call or a method. So we should be able to handle that, I guess. What was the question?
If whatever you're doing with your magic optimizations could make the cost of cooperative equality less prohibitive.
Okay, so you're saying that it's costly because there's always a virtual dispatch?
Yeah.
Okay, so the thing is, we usually have receiver type profiles which are bound to a specific method.
Mm-hmm.
But they're not context sensitive in the sense that you have a different profile for the entire stack. This is something that the VM doesn't give us, but it would certainly be nice to have. Right? If we had this, we could probably optimize certain code patterns much better because we rely on receiver type profiles a lot.
That would be fun, yeah.
Yeah. So if you have a concrete benchmark on which this is problematic, we would be very interested to.
So do you know any ref map in the Scala collection libraries?
The what?
Any ref map. It's a class in the collection libraries, and it's specialized to not do cooperative equality, so you can compare like hash map to any ref map.
Okay. Yeah, so I don't know too many. Maybe we can talk offline, so you can point me to the concrete thing.
Thank you very much. It was interesting. I just wonder for the performance evaluation, is in the blue bar that you showed the time that you measured, is the just-in-time compilation and the whole techniques and transformations, is that time included there? Because I think that also costs something to do that, and there must be some break-even point where it pays off.
So it's not. I was showing. Sorry. So I was showing peak performance. So I didn't include warm-up. Actually, our warm-up is slower compared to the C2 compiler.
Sure.
It's not by a lot, but you can feel it. For example, if the C2 compiler needs one iteration of the benchmark to warm up, we need 2 to 3.
Sure.
We actually track these warm-up curves. I can show you also offline to see.
Can you say something how much this is? Is this a few milliseconds or seconds, or just to have an impression of that?
I would say 2 to 3x. That would be my guess. Our warm-up is 2 to 3x longer compared to C2s. But it depends. I can show you concrete graphs.
Thank you.
There is. Sorry, yes. Last question.
You mentioned that some of this analysis is better to be done via a static compiler instead of a JIT compiler. I was wondering if you guys explored any usage of basically if you know you have similar workloads of using profiling to sort of provide some of the information you might have at the JIT compilation at static compilation time, right? So if you essentially know hey, you have let's say a server workload and you know you're going to get similar code that's JITted, then maybe you could take some of the profiling data you have and use that as part of static compilation initially.
Right. So we actually use this compiler as a just-in-time compiler mainly, but we also have an ahead-of-time compiler project, which uses the same compiler pipeline, but it has different hooks under the hood. And this one, actually, the way that it generates code is that it runs code within the JVM, and runs all the static initializers, collects receiver type profiles and branch frequency profiles, and then it proceeds to actually generate the code assembly, and it uses those profiles that it gathered. Now you can actually vary how long you're collecting profiles or where do you get them from. And for this project you can do that. But that's a separate JVM implementation, which is called SVM, it's called Substrate VM. It's basically used on the same compiler infrastructure, but it has an ahead-of-time compiler.
Yeah.
Okay. It's actually, it's not open source, but it's open in the sense that you can download it and play with it from Oracle web pages.
Okay, let's thank our speaker again. And